Okay, hello everyone. Today we are going to present our project called Rate-Constrained LDA with multiple sensors. Our group members are Yichong, Hongyang, and Simon, and Yuan Li. Our project is motivated by the brain-computer interaction application. That is, for a patient who is unable to move his hand, we put a lot of sensors around this patient's brain so that to collect signals from his brain and send all those data back to a fusion center to do inference task. For example, we can classify this patient's hands moving to the left as class 1 and moving to the right as class 2. Then the inference task becomes a two-class classification task. A challenge of this kind of distributed sensor network is that at the fusion center, what we get is not the real data, but context data. That is, for every sensor, we need to give certain amount of rate for the sensor, so that to context its data first, and then send all those context data back to the fusion center. But quantization, by definition, is to map a continuous set of values to finite discrete set. So to solve the problem of intuitively, if we give more rate to the sensor can quantize its data more accurately, so we can get better estimation of the data. But if we give a lot of energy to those sensors, it consumes a lot of energy during the transmission period. A method to solve this problem by Mazon is to find a good rate allocation strategy. That is, if a sensor's data is more relevant to the inference task, we assign more rates to the sensor. If a sensor's data is less relevant to the inference task, we assign less rate to the sensor. Then the problem becomes like this. For two-class classification task, this is the prediction error probability. Our goal is to minimize the prediction error probability subject to the total rate is less than or equal to a total rate constraint R. To simplify our problem, we first consider the linear discriminant analysis as a classifier. And we assume that the data of each sensor is independently Gaussian distributed. Their means are different, but their variance are the same. And for LDA, we compute the W transpose times the input data X minus a threshold mu. If they are less than or equal to 0, we classify the input data as class 1. If it's larger than 0, we classify them as class 2. And then my partner Yichong will introduce you our improvement on this problem.
So we first introduce our quantization method in our work. We use a simple code for quantization. That is, we use a code book like this from -b to b, and the interval is of size delta. B is the maximum quantized point, and delta is the unit length. A length of the interval. We quantize a real number by the nearest quantization point. We give an improvement over the previous work by using our new quantization method. The previous work approximates the misclassification probability by this amount. This is related to the LDA, and use the alloy code to quantize Gaussian probability. We use our new quantization method to remove the correlation between different sources and then obtain a better bound. We choose C such that with high probability that data lies in the region this one. That means, for example, we choose C equals 4, that is 99.9% probability. And we use B like this and delta like this. That means simply 2 to the R quantization points. We add a dithering noise that uniformly distributed in minus delta over 2 and delta over 2 before quantization. So this is our final quantization function. We can prove that under our quantization method, the noise of different variables are uncorrelated, and MSE is less than or equal to delta square over 4, providing that we give at least one bit to iterate each source. So under our quantization method, the best rate allocation is to like this. And so, well, lambda is selected that the total rate is constrained to R. The total mean square error is like this. We can compare our bound and the old bound in the related work. The relation is like this. You can see that it's exponential to the total rate R. So that means if R is reasonably large, our bound will be exponentially better than the previous bound. Then we'll introduce another improvement.
So each one introduce a case for if we know the underlying parameters. So if we do not know the underlying parameters, here's our algorithm for first for training, then for testing. So in the training phase, we first use the initial code, and we quantize it into x tilde, and we have n such training points. The fusion computes the sample mean and sample variance based on this quantized data points. Then the fusion design a new code based on the estimated mean and variance. So in the testing phase, we quantize each data using the new code, and we classify each observation based on the Bayesian rule. So here we introduce some theoretical guarantees. So this is like optimal classification error, that if we know the parameters and there's no quantization error, the classification error is like this. And so here's our theoretical guarantees. So if we have enough samples, that is n, and if we have enough rays, that is there. And then we have the following bounds. So you can compare these two classification error bounds. So inside the Gaussian tail function, we have additional epsilon, and there's an additional delta outside the classification error bound. That is to say, if we have enough training points and we have enough rays, we can approximate, or our classification error is close to the optimal classification error.
Okay, we now move on to the experiment section. Here we compare our methods with no parameter with the original methods. On the toy data, the synthetic data are generated as follows. Here, 100,000 data points are used for training the LDA classifier, and another 100,000 data points are used for the testing performance. There are in total 100 sensors who are independently Gaussian distributed. The means of the sensor is over I-squared distribution across sensors, and the variance is over exponential of I distributed across sensors. Here the blue line is our method, and the green line is the original method. You can see that given a fixed total rate, our method is significantly better than the previous result. We also compare our methods under the unknown parameters with the original method with the same setting as the previous experiment. Here also the green line is the original method, and the blue line is our method. You can see that when the total rate is relatively small, our method is not better than the previous result. However, as the total rate increases, our method is significantly better than the original method. This is exactly consistent with our theoretical prediction. Okay, now let's summarize our presentation today. Here we propose a new quantization method. We also design new algorithm for LDA-based quantized data classification. We also established theoretical analysis with better bounds than the previous results. Our experiment is exactly consistent with our theoretical prediction. In the future work, we may extend our method to the multi-class classification problem or regression task. We may also change the LDA classifier to other state-of-the-art classifier like SVM and so on, and also establish some similar analysis as our presentation today. That's all. Thank you very much for your attention.
So we have time for a few questions.
Why did you generate the synthetic data the way you did?
Because we first want to test our methods in the synthetic data, and later we will do that in the real data.
Oh, I just meant why the choices you made for the distributions used to generate the data. What was the background basis for that?
Because by using the toy data, we can generate the data satisfying our assumption in our theoretical analysis, and then we can test whether our theoretical analysis is true.
Okay, thank you.
Okay.
Other questions?
So you didn't test on the real data yet?
Yes, but we will do that later.
Okay. Okay. So you just didn't get, you just ran out of time.
So I have one more question. So you mentioned that your original motivation was BCI, right? Brain computer interfaces. And how close you are to your goal now?
Sorry?
So your original motivation was to work on BCI data, right? So, and my question is how close you are to achieve that goal?
How close? In the original paper, it assumed the data is Gaussian distribution, and
so my question is more like that. So your motivation was that you want to work on the data from brain-computer interfaces, right? Like I don't know, it was EEG scan maybe, or
yes.
right? And my question is, so how close you are to achieve that goal you originally had?
The related work has worked on the PCI data. So, well, this is an improved result of the original work, so it's probably will.
So we have a new rate allocation strategy. If we use our original, like naive one, just uniformly distributed rate to all sensors, then the classification is like 50 something. Then if we use our new strategy, like
so on which data that's the
I think on the real data, it achieved over 90 accuracy, but under a very low total rate constraint. So originally the BCI used a lot of total rates to do the classification, and it has over 90% accuracy.
And can you tell me more details about that data? What was the data there?
The data, you mean how to collect the
What was the data? So what was the
data
recording?
is the EEG.
But what was the task while they recorded? And
The
what?
task is classify a patient's hand moving to the left or right.
Okay.
So if it's left is class 1 and right as class 2. And we allocate thousands of sensors around the patient's brain. And
Was it thousands?
sometimes tens of thousands of. And
So it was not EEG.
it's not.
It was not EEG then, was it? So with EEG, thousands of EEG sensors. Okay,
I read the original papers.
maybe.
And then, let's see, like originally we give a lot of rate, they give a lot of rate for those sensors, and it has over 90% accuracy. But using the proposed method, we just give like less than 100 rates, total rates for sensors, and it still achieves the same accuracy.
Right. Any other questions? Then thanks again. And, let's see.
Thank you.
One more question. So please on your form, so somewhere write a number to like your overall score, say from a 1 to 10 scale. Like 10 is say best paper about that technique. 1, please take this course again next semester. Okay, so somewhere like that. This one.
Is there an order for?
Yeah, so next, who's the next thing?
Yeah, the adversarial net.
Okay.
Of course it's on the side.
No, this.
So we can just choose the Is this on? Yeah. Cool. So our project, hi guys. So our project basically deals with. Just a minute. Sorry about that. All right. So our project basically deals with generative models in general. And so the title is Learning with Generative Models in Vision, and our teammates are Hayden, Kenneth, and myself, I'm Dipon. So first up, what are generative models? Generative models in the context of vision are basically models which try to generate novel images and automatically, and these should be plausible in the sense that they should be realistic looking. So there has been more of a recent interest in vision community. Over the past years, I mean, there were some models like autoencoders and RBMs working with MNIST and datasets like that, but recently we have graduated onto CFAR and Toronto FaceNet, Toronto Face databases. So basically, why would we ever actually use a generative model? So one reason could be pure graphics. You could say that, okay, I can generate an image, maybe that's somewhat useful. Whether it's not practical, it depends on the quality of your images that you're looking for. In the context of machine learning, it's kind of important. This problem is really important from the context of representation learning as well. So if you can actually have a good generative model which can generate good images, good looking images, then you could say that you have learned a good representation of images in general. So in our project, we basically try to use this representation for a classification task. We see, okay, once we have a generative model, and we try to use this in some other task which has not been pre-trained on, how do we do? So there are multiple approaches to generative models. The most popular right now is generative adversarial nets, which is also our focus of this project. We will go over this in more detail. There are multiple variants of this, such as Laplacian pyramid generative models and adversarial nets, and MMDs-based adversarial nets, which also change the loss function a bit. Traditionally, there are autoencoders and its variants, and of course, the restricted Boltzmann machine. For evaluating generative models, there are actually multiple methods. It depends on what you really are looking for, what you really care about. So the whole idea, the basic primary goal is to estimate a distribution. So you could use something like a Parsons window or kernel density estimate followed by log likelihood, and that could be a loss function. Or you could have something like more of a qualitative evaluation in the sense that, are your images real looking? This could be more of a pure graphics, from a pure graphics standpoint. All this is really hard to do that in practice. So our project, we take a more specific route, slightly different. What we say is that, okay, once you have a generative model, how useful is the learned representation for classification for another different task? So that's the novel idea of a project. So what we do is we take a pre-trained network, and then we try and fine-tune it on a different classification task. Do we do better than a random initialized network? So now we move on to explaining what generative adversarial nets are.
So basically, what the adversarial approach to creating a generative model is to have it compete against another neural network. So we take our generative neural network, and then we have a discriminative neural network, which is trained to figure out whether an image is real or generated by the generative model. Minimax, the discriminative net wants to maximize its own accuracy. The generative net wants to minimize the discriminative net's accuracy. So noise goes into the generative network. It generates a set of images. We, with 50% probability, show the discriminative net one of the real images or fake ones, and it has to figure out, or it has to tell which is which. Then we backpropagate the the accuracy of the discriminative network back through the generative network. And we do this, iteratively. So I believe we did one epoch for each, going back and forth. One subtlety that we attempted to integrate was using the class label from CFAR 10, and then our discriminative task finally was going to be CFAR 100. So including that extra feature was another thing we included. So the approach, we used a multi-layer perceptron because that's what was used in the paper we were building on, or the paper we were primarily building on. So basically, this is mostly just to show what the inputs and outputs are. So input here for the generative network is noise and then an image. For the discriminative, it's that image and whether it is real or generated.
More thing to know.
So.
We have time for some questions.
You used discriminative network which decides whether the generated image is real or not to train the whole system, right?
Yeah.
So let's say my model, let's say my generative model generates an image which the discriminative network thinks is a real image, but it's still going to count that as an error, right?
Yes.
And it's going to backpropagate it, probably change the weights when we don't want it to in that case.
Yeah.
So you're saying you're worried that once the generative model starts generating real images.
Yeah, so I just want to understand the iteration between using the classifier on top of the generative model.
So if the discriminative network thought that a generated image was real, that would be treated as an error that would be backpropagated through the discriminative network, and then the overall accuracy of that network would be the backpropagated through the generative after we run the data set through it.
So the idea is that convergence, the generative network will have exactly learned the image distribution, and so there will be an error at the end, but it's not going to be able to change anything.
So the ideal accuracy for the discriminant network is 50%. It needs to come down to 50%.
And there is actually convergence proof, but it's actually not that convincing because it doesn't hold under how the models are actually trained, but you can look at it if you want.
How do you choose the patches?
That was someone else's work. That was just an example of
that was just
a weak label.
Yeah, that was just to give an intuition for what the approach is supposed to do.
What is the next step when you are actually looking at the final result, right? What is your next step?
Changing the network topology or network architecture.
So actually, there's been some really cool recent work that generates literally a few days ago.
Yeah, a few days
that
ago.
generates much more realistic looking images. So it might be nice to actually do this for like a non-trivial data set like ImageNet and see if you can get state-of-the-art unsupervised learning results on ImageNet.
They did get state-of-the-art results on CFAR 10. They used deep convolutional network.
It's convolutional, yes.
Yeah. So the problem, I can go on for a while about how there's been issues with reconstruction with convolutional networks. It seems like they might have solved the problem, but anyway, that's not at all in the scope of this.
But yeah, that was literally like 5 days ago that this paper came out.
Basically for ICLR.
What's the name of it?
Unsupervised representation learning with deep convolutional generative adversarial nets.
Other questions?
A question about the final experiment.
Yeah.
If you train on,
Which slide? What about this one?
So where?
The final plot, yeah.
Yeah. So if you train on the training data plus the generated data, what happens with trying that, or does it regularize it the way you want the model to be regularized, or it sort of pulls the model and goes down?
No, we didn't use the training data set at all in the final experiments.
But that would be interesting to see if.
Yeah, no, it would. I suspect, based on this, I would suspect it would almost be like if you added half of your data be noise, because it doesn't look like.
Because it's well known that if you add noise to the data, it regularizes the model in general.
Yeah.
So you sort of expand it and make it more intuitive.
Right. So I guess the idea of this experiment wasn't so much to do well in the final task as to figure out how well this generative network actually figured out how to make images.
So I know it was not your final goal, I'm just curious, that on CFAR 10, what was your best classification accuracy and how does it compare to the state of the art?
CFAR 100, you mean?
CFAR 100.
It's, what is it, 30?
So yours is
Ours gets to like 30, I want to say 30% accuracy.
And do you know where the best is?
It's around 60 to 70, I think. So I guess the problem is the state of the art doesn't use a multi-layer perceptron. That's really,
Yeah.
so hopefully,
Well,
that's one of the reasons why I don't like the CFAR 100, because it really isn't like other image data sets. Like ImageNet, state of the art, is a convolutional network. So that's really where we want to get to. But the problem is, for CFAR 100, it's so small and there's so many classes. You have to do sort of weird tricks to get high accuracy. So this was more just to show that this approach makes sense.
Yep.
A question about the term generating model. You mean the generating model, the model which is able to generate image, or you mean a model which models the joint distribution?
Sorry, could you say that again?
So
Yeah.
normally I'm confused because generating model normally means a model which models a joint distribution, but it seems here it's a model which can generate images.
So generative model in this context is one which can generate images, which you can sample from that distribution. But yeah, it would actually model the joint distribution
And
in
could
general.
you tell me what's the exact model you are using in the experiment? On the
Oh.
Yeah, multi-layer perceptron.
Multi-layer perception.
Yeah.
Okay.
And the way you sample it is like with a random seed. That's it.
Last question.
So what exactly is the benefit of having this generative model versus an autoencoder type of thing?
Oh, people have worked with autoencoders for this task.
Do you have any comparison of what works?
Well, I mean, do you mean like why not use an autoencoder as a generative model?
Yeah, they just keep the decoder as the generative model.
Well, that's sort of the approach. So there's sort of a subtlety there on autoencoders versus variational autoencoders. So variational has a sampling step, whereas an autoencoder is literally it just does a nonlinear transformation to some space and then out of it. So variational autoencoder is basically that, where it encodes into a space, but then there's a sampling procedure. So it is. The idea is if you want to have a generative model for images and you want to generate new images every time, you need to somehow randomize it so that you get different images every time. So that's sort of, does that answer your question?
Yeah, it's an approach people have taken. It's a valid approach to this. Currently, as of a few days ago, the state of the art here is the generative adversarial.
Okay, so we probably does get better results.
Yeah.
It's not really clear why the new results are better right now. It could just be that, like they had a bunch of changes. Like they did batch normalization and they used an all convolutional network, which is like a new thing. So it's possible that if you use those tricks in variational, suddenly variational will start looking good as well. It's not clear at this point.
Thanks.
Hi everyone, my name is Che, and this is Paul Wei, my teammate. And the target of our project is to predict drug synergy effect. To begin with, let's talk about what is synergy. The combined effect of drug A and drug B on cell can be modeled by the additive effect of drug A and drug B plus an additional term. And this additional term is called synergy. And let's see an example. This figure shows that additive effect of drug A and drug B is equal to the combined effect of the drug A and drug B. So this figure shows no synergy. But when it comes to this figure, we can see that the combined effect of drug A and drug B is significantly larger than the additive effect of drug A and drug B. So this case have a synergy effect. And why do we want to predict this effect? Because if we can predict synergy effect very well, then we can help prevent deadly drug combination side effects, or we can help develop new drug combination therapies. So our data set is obtained from the synergy prediction dream challenge. And so we have a data matrix for each cases. For each data entry, we have this is a cell lift rate based on different therapies. So at first, we will have 100 cell lift rate with no treatment. But when the dosage increases, we can see the cell lift rate decreases, which shows that the monotherapy effect of a drug, because this row and this column have only one effect of a drug. And then this gray part is the combined therapy, because it has the effect of two drugs combinations. So for the data in training set, we will have the full matrix. But for the data in testing set, we will only have the monotherapy data. So if we can predict the lift rate here, then we can predict synergy very well. And so this is a formal problem definition of our problem. So as we have talked about, the observed effect can be modeled by the additive effect of two drugs and their synergy. So we can obtain synergy by minus additive effect from the observed effect. And then you will get a synergy effect matrix. So, and then to get a synergy score, we perform integration on the matrix. So we'll get one real value to as a synergy score to characterize the synergy effect. Then we have tried three different modeling strategies. The first strategy is just a simple curve fitting of the monotherapy data. So this is a model from literature, and it assumes that the lift rate curve is decreasing and has a sigmoidal shape. So we can see that S is the survival rate here, and D is the damage due to the cell. So when the damage increases, the survival rate is decreasing. And these researchers have mathematical models here. So we can fit the monotherapy data and learn the parameters here, and then we can predict combined therapy data with the learned parameters. And this model serves as a baseline model. And before we get into the next two models, we need to talk about some little biology things. And besides training set, we are also given gene expression data. So we can see that it is a cell feature. So for each cell, we are given a vector of gene expression data. Then we want to apply this data into our model. So we need to find the drugs, the relationship between genes and drugs here. So as we know, drugs are designed to help regulate the functions of proteins. And proteins are generated from a set of biological functions from genes. So we can claim that drugs have an implicit relationship with genes. So it is reasonable to use these two features together. And then this comes to another baseline model, which is naive regression. We have built a naive feature vector, which only contains two drug features and gene expression data. And the idea is one of assumptions that drug vector is very sparse because drug only designed to regulate a small number of proteins. So, and to obtain sparse values, we use lasso regressions. And then we use RBF kernel and polynomial kernel with degree 2 to do the regression. Okay.
Okay, then I'll talk about our main contribution, which is the locality model. We see a lot of curve fitting, but why curve fitting? How we need to choose a curve? For example, if we want to predict the value in the rectangle, then maybe we can choose an anchor point. For example, in this case, is E beta. And let's observe the value below E beta. We'll see that inside the leaf rate matrix, the fluctuation of the leaf rate is actually very similar to the monotherapy of drug A. So if we choose E beta as an anchor point, we can simply simply minus the damage from the monotherapy to predict the value in the square. To be more specific, we want to choose a minimal of E alpha and E beta because we know that the drug combination will do more damage to a single drug, usually. And the damage here is 100 minus 90, which is 10. And we want to predict the value in the square by the anchor point minus a scaling factor times the damage. In this case, the result will be 62, and it is similar to 57. So the point is that we want to learn the scaling factor to minimize the synergy. Okay, then if we want to predict on drug A and drug B, we want to predict the leaf rate of drug A and drug B on the cell C, then we can model the leaf rate by this equation. The E alpha is the anchor point that we choose, and the middle is a scaling term, and the final is a damage term. So AB is a drug vector, and C is given is a cell gene expression or expression group. Then the scaling factor is modeled by two terms. The first term is about the drug-drug interaction on cell C, and the second term is just a linear model of drug B. To solve this problem, we could model this as a localization problem, and we solve the L1 regulation of the drug vector plus the loss from the monotherapy and the prediction of the total synergy. We want the drug to be sparse because we know that each drug only attacks on very few binding sites. Okay, the full problem is like this. Then we know that the variable here is A and B, and all other things given. So if we look at this equation, with this problem, we'll find that this problem is not convex. But if we fix all the variables and just move one variable, one coordinate, for example, an AIK, we'll see that it is actually a L1 term plus a quadratic equation. And this is actually similar to the matrix variation, and we can solve the one variable problem very smoothly. We developed a proximal coordinate descent method for this problem, and we use a dynamic programming technique to reduce the complexity from sugar to the number of features to linear to the number of features. And the number of features may be very large because we may want to use all the genes or some 0.2 expansion of the gene to model the gene-gene expression, gene-gene interaction. Okay, then here's the result. Before we introduce all the results, we must want to mention that the organizer shows that when they are redoing the experiments, the best correlation between the same experiment is 0.5. So we cannot apply more than 0.5 experiment in our data. Okay. So we obtained this data from, we obtained this result from the 5-fold cross validation from the real data. And if we use simple regression model, use polynomial kernel or arbitrary kernel, we'll obtain a 0.22 correlation. And if we use the literature, the damage additive damage model from the literature, we'll obtain 0.16 correlation. And for our base model, the locality model, if we just omit the scaling term, we'll obtain a 0.21. And if we use the whole model, full locality model, including learning the skeleton, we'll obtain 0.28 cross validation. Correlation. And we'll see that the training error here, the correlation in the training error is actually approach the limit of the experiment limit of experiment correlation. And what is more interesting, we find that we actually use very little number of features, so the L1 regularization work. If we use some simple gene groups from, for example, Go model, we'll have an average non-zero term of 8. And if we use the poly-2 expansion of these gene groups, we can actually achieve the 0.28 performance by only one non-zero parameter for each of the drug. So here's a conclusion. So our conclusion is like this. We designed a new locality model without using the curve fitting. The advantage of the locality model is that we do not need to worry about which curve to choose. Maybe your curve is not sigmoid, even it's another curve. And the second point is that we found that the although poly-2 expansion will bring a lot of feature vector, we can actually use L1 regularization to reduce the number of non-zero feature effectively and without harming the general performance. And the third conclusion is that we designed a proximal coordinate descent method for the kind of factorization problem. And we have linear complexity to the number of features, so we can do a lot of feature engineering. So there can be a lot of work to do on modeling the cell features. And finally, this work is actually a systematic study of the synergy model without using much domain knowledge, because we only use the cell feature. So maybe we can use more domain knowledge in the future work. Okay, thank you for listening.
This is the data set was coming from a competition.
Yes.
And how did your algorithm rank in that competition? Is it still an ongoing competition?
Yes, it's still ongoing, and we can only submit three times each month. So we did not submit many.
And is there a leaderboard there? So do you know where you are?
Yes. In terms of global correlation, we are in top 10, but of 100 and more teams. But yeah, there's room for improvement.
And what's the deadline when does the competition finish?
In February.
Very good.
Okay.
Questions?
This is very interesting result. So in the result it says that after the optimization there's only 1.0390 feature per drug. It means the optimization formulation should be quite smart. Quite interesting what constraint in the optimization which leads to the sparsity result.
Actually, just the L1 term here. So we can, this lambda mono and this lambda combination is a balancing between the monotherapy and the combinational therapy. We want to learn a feature from the monotherapy because we only have about 2,000 combined therapy experiment, and we had a lot of monotherapy experiment. So yeah, if we turn the lambda term to smaller, then the non-zero term will be smaller.
So the first term in your optimization is a regularization. The second and third term is the fitting term.
Yes. Sorry.
Go ahead.
Maybe I'm misunderstanding something, but the sparsity seems like a little bit different goal than drug synergy. So the less drugs you use, the less the synergy will be between the drugs.
We assume sparsity because our drugs are designed to fit very specific proteins. So the proteins the drugs have effect will be very small number. So that's why we assume this is sparsity.
But in the final result, we have average number of drugs used is 1.03, which means like you use one drug per link, right?
No, it's more like that. 1.0 is more like the drug feature only has one for each of the drug. You only need one non-real feature to respond to the cell features.
So it doesn't mean that you use only one drug for that cell?
No, it doesn't mean that. It means that it only reacts to a very specific cell feature.
How would this translate into the number of drugs that you eventually sort of combine to treat that cell?
The number of drugs?
Yeah, I mean, can you translate this feature back to the drug space when you select specific drugs?
We know that in this case, 42 case, the feature is a gene grouping.
Yeah, gene grouping.
And the 42 feature is actually like the drug interaction to two of the gene. So we are modeling on that.
How do you generalize? I just wonder whether your model can be generalized to more number of drugs.
You mean the complexity part?
Yes,
or?
yes.
Okay.
Especially when you deal with drugs that have adverse effects on each other, or more complications anyway.
Can you state your problem again?
Yeah, just
Sorry.
basically raise the dimension of number of drugs.
Number of drugs is about 119.
119.
Huh?
Yeah, I'm just checking whether increasing the dimension will actually, how will you deal with that in your model?
The complexity is linear to the number. Yes, linear to the number of drugs. So yeah,
So
it actually
how do you
scales.
bring the big O from square to medium?
And if we do the dot term here every time, then if we cycle through all the features, then it will naturally come this square to the number of feature term. But if we notice that if we update AIK sometime at one time, then we will see that if we keep the prediction here, we only need to update a single term AIK, CIK in each of the model. Yeah, okay.
Yeah.
So this might have been what you were mentioning, but in the grid, you're modeling the synergy between two drugs. Can you do it between two or more, like 3 drugs or 4 drugs?
We haven't designed that, but we haven't designed for that. But for 3 or more drugs, then it will be a model including more polynomial term of the drug combinations. Yeah. And for 2 drugs, it's actually like matrix federation, but for more drugs, it may be like tensor decomposition, and I don't know if that will work.
So the lambdas there, you chose them by doing some cross validation. How do you choose the lambdas?
We choose it by hand.
By hand.
Yeah. We did search a large lambda. So the lambda model in this model is 0.001, and lambda code here is like 10.
Just because they work better. Did you run a lot of lambdas? Then
it works better in cross validation. So we already use cross validation. We can actually use cross validation to choose lambda, but actually training lambda will affect the number of non-zero, but will not affect the number of cross validation much. Okay. Any question?
Thanks.
Okay.
And we have one more presentation today.
I don't know if I have this book. Are there other connections? No, I don't.
Does anybody have a Mac adapter for VGA?
You don't have one of these on yours?
No, I need one too. Yeah, we don't have a way of plugging this in. Yep.
Is it possible? Is it
It's,
PDF?
it's online. If we
online.
could borrow
Yeah,
some.
so can someone borrow a laptop? But
We
should be
need
not
the Mac
right?
adapter, so.
Or a,
You don't have an HDMI.
No, I don't think so. Unless I'm an idiot.
It doesn't look on.
so meanwhile, there will be a machine learning lunch talk at noon from a postdoctoral fellow at the University of College London. And, his presentation will be on distribution regression. He's a postdoctoral fellow of Arthur Gratton, and he did lots of interesting stuff with kernels, and you might be interested in it. He also has some time to meet you if you are interested on Tuesday and Wednesday. If you want to meet him, so his name is Zoltán Szabó. If you want to meet him, then please send an email to Sandy, my assistant, and she can schedule a meeting with you.
Got it. Thank you.
Right, so the talk is on the 6th floor, the big room, at noon. And lunch is provided.
Okay, so I'm Ryan, this is Jay, and we are interested in studying properties of neurons, particularly receptive fields, in the visual cortex using natural scenes. So in visual neuroscience, what you're generally interested in is taking a stimulus and correlating that with some neural activity. And typically with neuroscience experiments, you use very simple stimuli. So on the left, we have a very simple stimulus, and you might be able to vary one parameter in that and correlate that parameter with the neural activity. But it's been shown that when you show natural images, the results that you get from simple stimuli don't generalize to these natural images, and so you can't predict the neural response very well. So what we'd like to do is come up with methods that will allow us to predict the neural response to natural stimuli. So just to describe our experiment, we have a monkey that is looking at an image on a screen, and multiple images are flashing, and he's free to gaze wherever he wants on the screen. We then record the electrical activity of the neurons and have a threshold here, and we measure the number of times that the electrical activity crosses that threshold and count and bin that quantity into a number called spike counts. So there's some challenges with this. If the monkey's free to look all over the screen, it's difficult to know exactly what part of the image the neurons are responding to. And we're in particular, so we're interested in a particular aspect of neurons called receptive field. So the red spot is where the monkey is fixating, and the box represents the part of the image that the neuron responds to, and this is called the receptive field of the neuron. And this receptive field can move as the fixation point moves around the image. It's unclear how this receptive field changes during eye movement, but we know that at least it's fixed during when the monkey is staring at a single point. And so what we can do is we can take image patches from various points when the monkey is focusing on a particular point in the image, and we can correlate that with the neural activity. So what we want to do is we want to develop a model that will allow us to predict the neural activity of these spike counts from an image patch on the screen.
So one of the biggest challenges to fitting receptive fields, even in general, is that you're often limited in the number of trials you have, either because the monkey gets bored and stops performing, or you lose the signal on your electrode. And then here, especially if we're using natural scenes, you have many more free parameters to fit because you've lost your simple stimuli. And so overfitting is a big problem. So two of the ways we can get around that are to apply biological priors on the receptive field. Biological in that they reflect some kind of assumptions that we have about what the receptive field looks like. And then we can use evidence optimization instead of cross-validation to pick the hyperparameters for those priors. And so our novelty in this project is to use this linear regression method and apply them to later areas in the visual system and using natural scenes. And so neural responses are very nonlinear, but receptive field estimation often focuses on the linear components because you want to walk away with some kind of general purpose description of how the cell responds to images. So here, if we stack up all the image patches in X, and then we count the spikes in response to each of those, where our receptive field is W, which is just some linear weighting of each of the images. And if we assume that our spike counts Y, given the stimulus and receptive field, are Gaussian, then to regularize, we'll pick a zero mean Gaussian prior on our weights. So first I'm going to talk about some of the priors we consider, and then I'll talk about why this Gaussian assumption gives us some extra power. The first prior we look at is ridge, which is the simplest, and this is where each of your weights are just drawn independently with some common variance. So if you look at the cartoon on the right, weights 1 and weights 2 this is their prior covariance, it's independent, and they have the same variance. But we know receptive fields, often most of the pixels in the image are not going to correlate with the spike count at all. And so by allowing this variance to be independent for each weight, then you allow certain weights to go to 0. So here, if weight 1 has its variance shrinks, then weight 1 will be most likely 0. So ARG is a sparse prior. And then finally, this is the probably the best prior for receptive field estimation, but it's only previously been applied in auditory neurons, is AST. So this is where you relax the independence assumption of weights. And we want to do that because receptive fields are often smooth. So if one pixel correlates with the neuron's response, then nearby pixels should correlate similarly. So we want to fit this delta hyperparameter that describes how this covariance structure falls off with the distance between the two weights and the stimulus space. And one nice thing about ASD is that if you pick the delta at 0, then this just becomes the ridge prior. But as you increase delta, these are the prior covariance matrices, different levels of delta. So as delta increases, you get more and more smoothness in your estimation. And using, I guess generally you would do cross-validation and you would grid over your hyperparameter space. But here, by having a Gaussian posterior, we can integrate the likelihood and the prior to come up with a measure that reflects, regardless of the final receptive field estimate, what's the evidence for a given hyperparameter. So we can fit the hyperparameters first, given just the stimulus and the spike counts, and then once we choose those, get our W receptive field using the Gaussian posterior. So we did gradient ascent on the log evidence to pick these hyperparameters.
Right, so we tried doing this with our neural data, and it turned out that the neural data was actually bad in the sense that when you implant an array in a monkey, over time the array goes bad, and then the signal-to-noise ratio gets too much or too low, so you can't actually detect the neurons accurately. So we had to use a simulation. And this is a model for neural activity or for receptive fields that has been previously published. And in the past, it was used where you would model the neural activity, just neural response to simple stimuli, and you were able to produce spikes from that. So what we do is we input the pixels from an image patch that we pre-select, and then we apply the filter to that, and we produce spike counts. And what then we apply our model to try to predict where that image patch was on the screen. And we were able to, here are two examples where we were able to do that accurately. The red, so these, what we're doing here is we're going image patch by image patch, doing a grid search over image patches, and I'm showing the R squared here. And the R squared is highest at the point where the image patch was selected for the simulation. So we were able to recover the receptive field correctly.
Yeah, so once we've recovered the relative location of the receptive field to where the eye position is, then we want to fit the actual filter. And so we have 4 different models we looked at for the 4 priors I talked about before. And then we can also fit these in different feature spaces that are more biologically motivated. And what we want to know is how these different models perform given small amounts of trials and low signal and noise. So we ran a simulation comparing these models for various levels of signal and noise and trial count. And so the x-axis here are signal and noise, and each panel is more and more data, and the y-axis is just the median R squared across a lot of bootstraps. So the blue is maximum likelihoods. So you can see it's generally very poor, especially over towards the left, which is probably a reasonable amount of trials to get. And Ridge and ASD both do really well, even at really low numbers of trials. And this is fitting 256 parameters. So this is a setting where you have to do some kind of regularization. And ASD and Ridge seem really good. But if you pick out the receptive fields that these models are estimating in the simulation, this is a case where all 4 of the models do relatively well in terms of R squared, but they all have a completely different interpretation in terms of what the cell is doing. So maximum likelihood is doing just as well as the others, but it has no form. If you saw this as an experimenter, you wouldn't have any idea what the cell was doing. Whereas Ridge and ASD both look really good. ASD matches the original filter almost exactly, and that's because the original filter has smoothness in it, and ASD is able to recover that. ARD, because it's a generalization of Ridge, I would have thought that it would have done better, but you can see it's kind of setting too many of the weights to gray, which is 0. So it's kind of being too sparse, I guess. So yeah, I'm not sure why that is, but in ARD, we have as many hyperparameters as we have weights, so that's probably why it's not doing as well. Yeah, so the final challenge is that the area we're interested in, V4, doesn't receive, it goes through other levels of processing before it sees the image. So we considered doing receptive field estimation in a different basis. So in particular, we chose ICA. ICA filters are a really good match for what the primary visual cortex appears to be doing. So we just transform the stimulus into this space, which might be a good representation of what inputs V4 is receiving. And now if you do the same estimation in this space, you can see that Ridge still does really well. ASD doesn't make as much sense now because you don't expect there to be smoothness across your weights. But now Ridge is smooth, and that's because ICA is, we're now fitting fewer parameters than we were before. So there's some kind of implicit smoothness in this space.
Yeah. So just to conclude, Kate just mentioned Ridge and ASD. They performed better than the maximum likelihood estimate for finding the receptive field location. We can use evidence optimization to allow us to fit this model with a smaller number of trials, a more realistic number of trials, and we can then use the fit model to actually look at what the filter, try to recover the original filter, and ASD performs the best. But if we switch to an ICA basis, then Ridge actually does fairly well. So these methods that we've shown here, they work on simulated neurons. We would like to, in the future, apply this to real monkey data once we collect new monkey data on the neural array. And some other future directions we'd like to be able to track this over continuous time rather than just during fixation periods and then look during eye movements. Thank you.
How much does this sensor cost?
A sensor? I think it's about, the sensor itself I think is $1,000.
The UTAR is?
UTAR is $1,000, and you have to have a surgery to put the implant in, so it's upwards $10,000, $20,000.
So it goes inside the brain of the monkey.
Yeah, it goes inside the brain. It's very expensive.
Oh, I thought, because at first I thought the monkey data is kind of brain noisy. I was thinking whether we should replace it with human. No, cannot.
No, you can't.
Yeah. They do have UTAR arrays implanted in some humans.
With epilepsy.
Yeah.
Is there less invasive types where you can, for example, you can either movement you can track? I think that equipment just costs a few $100s. And then if you can have a less invasive.
That's the issue. Less invasive with high resolution. So being able to get single neuron resolution is very difficult with less invasive techniques. So EEG is good, but because it's non-invasive, but it covers tens of thousands of neurons per electrode.
Okay, so that means you cannot actually generate. You cannot generate your own data in a way. You still need to depend on these people doing stuff.
Right. Yeah.
So I'm just curious, how bad those results were when you used real data from the real monkeys?
It didn't fit at all.
Horrible. Yeah. So usually you should be able to just fit a simple linear model and get an R squared of around 0.3.
That data was just bad for your goals, or
No, just bad.
Bad in general. Yeah.
This was like a spare data set that no one had analyzed, and we thought that it would be this great goldmine, but no.
Yeah, there are standard methods for analyzing receptive fields, and so they have a separate experiment with the same array where they do the standard method, and it didn't work with that very well.
So where are those monkeys now? Have you monkeys?
They're so the monkeys are in over a pit. Yeah.
Questions? So I'm just curious, what kind of ICA method did you use?
Image ICA.
Image ICA?
Yeah.
It was a package. I don't remember what they were.
Okay.
Yeah. You set the number of filters you use, and then I don't think it was the fast ICA. It was something else.
Other questions?
Did you use any sort of eye tracking techniques to help recover the location of the fields or something like that? Or did you focus it on?
Yeah, so that's how we picked the image patches. Is they're so that we know where the monkey's eye position is every time, and so when in this graph where Ryan was showing, so all of these locations are relative to the eye position. So as the eye position moves, we're always looking at the same offset. So we have to have the eye tracking data to know, because the receptive field stays fixed relative to that.
Can you replace that part of the data with human tracking?
You could track human. Yeah. But you don't have access to human neurons.
Yeah, so you need
that's the
both
issue.
simultaneously.
Yeah.
Yeah.
Okay, yes. Okay. Hope you get your data.
So just one, so related work, I don't know if you follow Liam Paninsky's work. So I know that he did something similar. It's just he used active learning to estimate the receptive field of neurons, and that was pretty cool too. That so he measured the response from the monkey, and then based on that he changed the stimuli to show the monkey. And he tried to find that stimuli that activates the neuron the most. And so
Yeah, that's cool.
Interesting, yeah.
I haven't seen that.
Right, so you might want to look at that.
Yeah.
Yeah, that's interesting. Yeah. So it's like an experimental way to.
Yeah. And he did that online. So the stimuli, it got improved while they got feedback from the monkey.
Yeah, that's a big problem, because if you pick the wrong stimulus set, you spend all day showing it to the neuron,
Right.
only to find out later it wasn't driving the cell at all. So it seems useful.
All right, thanks. It was really great to see these very interesting presentations, and we follow this Wednesday with 6 more. So we have to be very careful this Wednesday on the time, because today we spend the whole lecture on these 4 presentations, and we will have 6 this Wednesday. So just be prepared.
Do we have like
You do. Right. So one thing we can do that please send your slides to the TAs, and then you don't need to change laptops. That would help to save some time.